Like we're good. Good morning, everybody. Today we'll be starting chapter 10, which is on gas laws. And so, really, in this chapter, we're going to be focused on understanding the behavior and properties of molecules or atoms that are in the gas phase. So, we'll start off by kind of talking about gases in general. We'll have a couple of properties that we're going to talk about. And then we're going to look at relationships between those properties. I like this chapter because it's very predictive. Once you understand the trends between the relationships of things we can talk about with gases, such as their volume and pressure, um, it really works out nicely. It's purely a lot of math. The math is very simple, though. There's really just, 3, 4 equations that we're going to be using, and they're all just simple division or multiplication. So um, it's a nice chapter in that. It's also a fairly short chapter, so this is good for us. Yay! So you can have your time not watching these videos and instead preparing for your exam next week, as I'm sure you're going to be doing anyway. Just like always, right? So we can go ahead and get started. Let's talk about gases. Um, we're going to kind of start by just looking at the state of matter as itself, and then we'll talk about quantities. We're going to talk about assumptions we make about gases a little bit later on, probably on Thursday. So today we'll just kind of leave those off the table right now, and then we'll bring them in next time. Miss Bailey, what are you eating? She found a piece of pasta. How unappetizing, like dried. Oh well. So gases. So gases are interesting state of matter. Um, and molecularly, we might describe them something like this, right? Where we have a bunch of atoms or molecules. We're going to see for this entire chapter the identity of our substance does not matter. A molecule of methane behaves the same as a xenon atom in terms of gas behavior. So we're going to see that all gases behave exactly the same, though we'll see next time there are some minor changes that we have to do later on. But generally speaking, the trends about gases are all the same, no matter what they are. And so we can describe it by looking at a particle of gas. They happen to be far away from each other, so that's one thing that we know. So they're far away from each other, which we can say in terms of properties makes it not dense. We know that air is quite the opposite of dense, right? It's on top of everything else. Remember that in terms of density, dense things sink to the bottom, and not dense things rise to the top. So I don't really know what the opposite of dense is. Um, we don't really have a term for it, but the density is low, we'll say. Gases are constantly moving. We might say rapidly. So we can see that there. These are also, because they're so far apart, they are very compressible. And that means that volume can be changed easily. And we know this because gases will always expand to fill whatever container they're in. And whether that container is a balloon, a gas tank, your lungs, a jar, whatever, any sort of container that we have a gas in, the gases will always assume the volume of that container. And technically, the Earth is a container as well, right? We have a bunch of gas in the atmosphere that's here by gravity. And so that's a container as well, although we don't really think of it that way. If you want to kind of understand this, consider like if someone sprays perfume in the corner of the classroom or whatever, we know pretty soon after the whole room is going to stink, right? Depending on the perfume, I guess, technically, but it's going to smell different, right? And that's because gas molecules have gone from one side and they're expanding to completely fill the entire room. And so maybe the room is our container. So gases will always assume the volume of their container. So they don't have a fixed volume of their own unless they are contained by something. So the gas in the atmosphere, again, technically has the volume of the atmosphere, but that's so big that we don't really consider it. We more consider the volume inside a balloon or inside a piston or inside your lungs, like like I've mentioned. So or a gas tank. So those are the volumes we're really looking at here. So these are compressible because they're so far apart. Um, and so if we want to think about quantities we can talk about with gases, that are going to help us determine its behavior. We have four that we're going to be talking about, and we're going to start with the newest one last. So I'm going to start with the three that we already know. First one we could say maybe will be temperature. Temperature, as we're going to look in more detail on Thursday, relates to the average kinetic energy. So the temperature release is the average kinetic energy of our system, of our gas. And we're going to see that this is essentially a measure of how fast the particles move. We can generalize it that way. We're going to look in more detail on Thursday about temperature. And we're going to see that there are probabilities of how things are moving. But suffice it to say that the temperature is a measure of the average kinetic energy, and that's just telling us how quickly things are moving. So a high temperature means things are moving fast. A low temperature means things are moving more slowly. I guess I should write temperature, shouldn't I? All right, so that's temperature. Let's use blue. No, we've just used blue, light blue. Let's talk about the volume, which we use the abbreviation V. By the way, the units for temperature, the unit we'll only use here is Kelvin. We are not going to use Celsius for anything related to temperature. We can get away with that with some of our thermochemistry and that sort of thing where we had delta T's involved. Here we don't. So there will be no, everything must be Kelvin for temperature. For volume, this tells us how much space the gas occupies. That's just the definition of volume, right? It's how much space something takes up. And we're looking that, again, really for gases, that is how big the container is. Because we don't really look at the gas itself. We know that they will fit whatever container we put them in. So if we know the volume of the container, we therefore know the volume of gas that's within it. The units for this, typically we're going to be using liters. You might see meters cubed. Just remember that 1,000 liters is 1 cubic meter. So don't forget that. That's one of our things or 1 centimeter squared is going to be a milliliter. So cool. Next one we know is the moles or amount of or let's just say moles. We usually abbreviate this with the letter N, lowercase. This is the amount of gas particles. And so it's important for us to be able to say, okay, well, I have two molecules that are in this container, or I have 20 kajillion molecules that are in this container. Um, it's an important consideration when we're talking about gases. So it's the amount of material that we have in there. Um, Generally speaking, we could talk about molarity of gases, though that's a little bit less common. Typically, we talk about the moles having to do with mass more often. So we typically will use molar mass as part of this rather than molarity or some other main of talking about moles. All right, and then the last one, don't they have like a green? These greens are ugly. That's too bright. That one. Okay, the new one is pressure, capital P, which will be our new one for us. This is our new quantity. So it's one that we're not going to be maybe as familiar with as the other three. Pressure is a force exerted over an area, and that's more a physics definition. For chemistry, we can kind of think about it in another way, or it's kind of just how frequently gas particles collide with the walls. So it's how quickly how often they're bonking into the wall, and that's going to end up causing a pressure over time. If you think constantly, we're living in one atmosphere of gas. That's a unit we'll talk about in just a second, um, and so we're being constantly bombarded by gas particles, quadrillions of them, all the time. We don't feel it, of course, because we're used to this. However, if we go into space, or we go, more than 100 feet below the ocean, we start feeling it. Um, and that's pressure either from the water, if you're underwater, 100 feet is about another atmosphere, or if you're in space where you have no pressure on you, definitely things feel different. So we're used to it. We're used to experiencing the normal atmospheric pressure. And so we're going to see that that's simply a measure of how much we are being smacked by gas particles. And this is something, again, all the time, very frequently. Units for pressure. Standardly, we talk about the atmosphere as a unit, which is 101,325 pascals. That's the SI unit, is the pascal, which is a Newton per square meter. So if you are familiar with physics, that's the unit there. So one atmosphere that we're experiencing right now is 101,000 newtons per square meter. So that's quite a lot, but it's what we're used to feeling. And this is about at sea level ish. We're going to see that there is some elevation that can mess with our pressure. Uh, Another unit would be the bar. We're going to see that one bar is defined as 10 to the fifth pascals. A bar is, I guess, another SI unit, System International. It's kind of our I don't know, unit standardization body. Usually in chemistry, we talk about atmospheres because that's historically what's always been done. However, in fancier, more advanced stuff, people talk about bars more and more frequently. In theory, or rather in reality, the bar was adopted as the formal correct unit for pressure by the International Union of Pure and Applied Chemistry in the 80s, but people still use atmospheres far more often than they use bars. But suffice it to say, if we were to combine these two, we're going to see that one atmosphere would just be 1.01 bars, so roughly the same, roughly. We have another unit, one that is more physically derived. We have the millimeters of mercury, and that's one atmosphere. That's something here. This is millimeters of mercury. And we'll talk about where this comes from in just a little bit. But suffice it to say, it's how much in a tube mercury will rise against atmospheric pressure. We'll take a look at where this unit comes from. I just want to go through all the units first, and then have them all in one place, and then we will um, look at where this definition comes from. And then we have one more unit that we use typically within the metric system, which is torr. And a torr is the same thing as a millimeter of mercury. There is a very slight difference between the two. In theory, though I'm not going to really enforce this, millimeters of mercury is something that is a measurement and therefore will have sig figs. Um, that's not to say you're going to ignore sig figs, but when you're converting between atmospheres and millimeters of mercury, I don't worry about sig figs for that conversion. All right, you still need to use your sig figs for your actual calculations and your problems, but in theory, an atmosphere is not exactly 760 millimeters of mercury, but it is exactly 760 torr. So you see there the 760.0000 millimeters of mercury. That's to understand that that comes from an experimental value. The exact value is defined for us. So we have defined 760 torr to equal 1 atmosphere. So that's an exact number, no sig figs there. Again, for this class, when you're converting between pressure units, I'm not going to worry about sig figs for that. However, again, I will worry about them when it comes to actual problems. All right, so those are our um, metric units. We have a lot of them. And we will use, generally speaking, we'll use millimeter of mercury and atmospheres for the most part, or torr. Um, and so bars we typically don't use as much, or pascals, but those are there. They exist. All right, non-metric units we have one we are familiar with maybe is PSI, pounds per square inch. Pounds per square inch. We're looking at about 14.6 psi is about 1 atmosphere, if I am not mistaken. Uh, it's something around there. If we want to think of something like your car tires, or your car tires typically are about 30 psi or so, 30, 35, a little bit higher if you have an SUV or a truck. Um, but that's about 2 atmospheres is the pressure within your tires. And so we're going to see that that's pretty common. Um, you know, PSI is a pretty standard unit for us in the US. We use PSI for things like pressure. We use it um, for compressors and things for mechanics. Often use pressures, hydraulic presses, all with pressure with PSI as their unit. Um, What other units do we have? Is that the only non-metric one that we use? Yeah, pretty much. So just be aware that's also a pressure unit. I'm not going to really worry about that because we're not going to deal with that in chemistry, but just be aware. Know of its existence. It is a pressure unit. So next time you're looking at your, um, I don't know, what would we look at? I don't know, maybe you have a gas tank or something. In fact, for my pool, I have a filter that reads pressure in PSI. So just fun stuff, I guess. Um, you may also see pressure. Uh, if you go get your blood pressure measured, you're going to see that you'll have, you know, um, ideally you'll have two blood pressure readings of around these values. Maybe not, hopefully not too much higher. For your systolic and diastolic blood pressure, you'll see the unit of millimeters of mercury with those. And so that's pretty common. In the US, sometimes we see inches of mercury. And that's just like millimeters of mercury, but millimeters is metric, inches is US for distance, right? So we see that 25.4, it would be 1 inch of mercury. And if I were to open my phone right now and go to my weather app, I can find this right now. Let's see what the pressure is in Ridgecrest if my app decides to load. Nope, I've got an ad. Look, I can do this mobile game or something. All right, that's enough of that. Okay, so let's see if we can't find the pressure. Aha! So, interesting. So this app has given the pressure to me in millibars. So if you see that 1,119 millibars. So interesting. This app does that. The Weather Channel app gives you inches of mercury. I know that much. So go figure for me using a non-Weather Channel app. But these are things that you'll see. So just like before, you can have centimeters of mercury. You can have millibars, like we just saw. We can have microbars, uh, kilobars, all sorts of things we can do. We can throw all the prefixes on these just like before. So let's look at the old school way of measuring pressure. So way back when, there was, in order to measure pressure, they had this bowl full of mercury. And the choice for that will be looked at later. And so what they did was they put a tube upside down into this thing of mercury. And they applied a vacuum, which is ideally zero pressure or a very small pressure. And so if we consider that gas molecules from the atmosphere, oh, I don't like these colors at all. There we go. We know that atmospheric pressure is always pushing down on things. And normally, if we, were to just take a regular tube and put it in a pool or something, nothing is going to happen because the pressure there's gas within that tube, right? And it'll be pushing down as well onto our system. But if we apply a vacuum, that means we have nothing inside. We have zero pressure inside. And so we have nothing pushing down. And so the mercury then ends up going up the tube. So the mercury ends up going up the tube against gravity. And so we have the opposite forces here. We have pressure pushing things up into the tube, and we have gravity pulling it down. So those two competing forces end up equalizing at some point, and that turns out to be at sea level 760 millimeters. So it's how far up the the tube in the what's called a barometer how far up the tube the mercury climbed against gravity. And so that's a measure of how much the gas or the pressure was pushing against the pool of mercury. And again, it pushes in, and so it will end up pushing it up the tube because there's nothing in the tube to prevent it from going in there. So this is called a barometer. And these are no longer used, of course, because mercury is a terribly toxic liquid and it evaporates pretty easily, and the gas is particularly toxic. So we no longer use it. Lost a little coffee there. We can see we can do the same thing with water. And you know what? Let's go and look on Google because I am terrible at drawing these, and it'll just be easier for us to see here. So if we look at a barometer, let's look at a mercury one first. Okay, so let's see if we can't find like aha. So let's see here. New window as always. All right, so look, I can buy all these terrible things. Okay. Barometers work like this. So we see that you have your pool of mercury, atmospheric pressure pushes down, which forces mercury up the tube against gravity. Again, it goes in there because there's nothing pushing against it in the tube. Normally, again, a tube, if there's gas inside, it will push the mercury back down because it will be equal to atmospheric pressure, so there will be no change whatsoever. However, if it's a vacuum inside, there's nothing to stop it, so the mercury goes up, and the amount it goes against gravity, in this case 29.92 inches of mercury, same thing. And if we try and look at a water barometer, we see that we can do these too, but for water, look at how many meters this thing is going to be. It's 10,000 meters. For oh, here's a good comparison. So mercury goes up. This is a wrong number. It should be 7.760 mercury millimeters. Look at the water, 33 feet. So I'm sorry, I read this wrong because this is a European thing. So that's 10. I'm sorry, this is 10,744 millimeters. The past one we looked at was that was 10.336 meters, and so that's about 33 feet. So versus 2.5 feet for the mercury. So you can use water, but it's troublesome. So 33 feet. No one's going to build a tube like that and pull a vacuum on it and watch the water go up. The reason for that is because mercury is much more dense, so gravity has a stronger effect on it, and so we can use a smaller tube. So you may also see inches of water or millimeters of water or whatever. Those are also pressure units. So that would be 33 feet of water for that. So that's enough of pressure units. Let's look at another device, a manometer. This one is much more experimentally used. Barometers are pretty much out of the picture. We now have electronics to do all of the measurements for us. So, but a manometer is still something that's used. It's used to compare pressure. And so you might have a tube that goes between two gas containers, and maybe they have little walls that separate them, and there's liquid inside. And so we have two gas samples with different pressures. Or they could have the same pressure. And so if we open these up, once they become open, I'm going to copy this. Once we open it, then the pressures will interact with this liquid here, and they might move it. They might move the liquid. And we're going to see here, we have a height. I don't know why I put delta. That's a height in there. And that will be equal to the change or the difference in pressure. So the height of your manometer, how high the water rises on one side compared to the other, will be your difference in pressure. And so it's important to note that the side that has lower will have more pressure because it's pushing down more. It's pushing down more, the other side is pushing down less. And so as a result, there's an imbalance there, and that's going to be the difference in pressure between the two. All right, and so we're gonna once again look at Google because my drawings look like, let's say this looks like ovaries. This is manometers are a little bit less anatomical, we'll say. So let's try again. Let's go ahead and look at a manometer. So this would be an example. I'll look at these much better drawings. Yeah. Here we go. So pulling against various things. If you pull against a vacuum, if you pull against atmospheric pressure, or whatever it is, the height is related to the pressure here. So if it's open to the atmosphere, you'll have, actually this is probably a better one. So if you have an open one, you have atmospheric pressure as your second pressure. Your pressure of the gas will exert its own pressure. Whichever one is lower, that one has the higher pressure. And the difference in height is going to be equal to the difference in pressure. So let's say this is filled with mercury. This would be 4 centimeters of mercury difference in pressure. And so it's simply a matter of looking at which one of these is going to be higher than the other one. All right, and so we're going to see that the pressures here are just related to these things. So if we take a look at an open manometer like this one is, that means your second one. Let me switch back. In this case, we had a closed manometer, so we're looking at the difference of pressure, and that would be the difference of pressure between the two, which would be the difference between pressure 1 and pressure 2. That would be your height. If we have an open one, now this is going to look like a kidney, like a nephron. But if we have this open to the atmosphere, in this case, let's make the again, we have our H here. This is our pressure of gas. Here is our pressure of the atmosphere. So it of course depends on like which one's going to be bigger, right? But suffice it to say, the pressure of your gas will equal your height plus the pressure of the atmosphere. So whatever that happens to be. So in this case, our height would be negative because the atmosphere is stronger. So in this case, it's negative. So because we have a loss of height, right? So we're going to see that that's what in the case of your gas having less pressure than your atmosphere, H will be negative. In the case where your gas has higher pressure than the atmosphere, H will be positive. So Because if you think about it, if you H plus ATM, if they're both positive, you're going to have a bigger number. But we can see here that the gas has a lower pressure because the mercury level is higher there. So you'll have to consider what the higher one is before making that determination. And so if your gas has higher pressure than the atmosphere, again, the pressure of your gas will be equal to the height plus the pressure of the atmosphere. And in this case, H is positive. So you'll just use whichever one is the logical one. So if you can see that your pressure of the gas is lower than your atmosphere, H will be negative. If your pressure is going to be higher than the atmospheric pressure, then H will be positive. So you'll have some problems where you're looking at manometers and you'll make that determination for which H, the positive or negative one, to use. All right. So fun stuff. So that's how we measure pressure. All this has been about measuring pressure. Alrighty. So um, that's our pressure measurement thing. Let's see what we can do with this. We're going to relate pressure to our other three variables now. Now, this is something I diverge from the book in this, and I diverge from a lot of chemists because a lot of chemists teach this section looking at pairs of things that were experimentally done in like the 1600s, 1700s, 1800s. Um, and they like force you to memorize the names of the scientists who did these comparisons, and it's I don't see that having any benefit to your understanding of chemistry. So I don't do that. What I do instead is I'm going to take your idea of logic, third grade physics. You think, these things make sense. Um, I'm going to use your logic, your own ability to conceptualize things to explain the relationships of these rather than using some old scientists from the 1800s. No offense to them, of course, they did good work, but that's not going to help you learn this. If you want to learn the history, go right ahead. You learn about Charles and Boyles and Gay-Lussac and Avogadro. They did all these experiments. But let's relate this to things that we already know. And so sometimes I do this with an analogy, and sometimes I don't. But let's look at pressure and volume. So remember that pressure is how often uh, gas collides with the wall. If we understand that, we're going to be able to understand the relationships between pressure and volume, pressure and temperature, and pressure and moles. So if we look at volume, I'm going to put our gas molecule into two different containers. If if the temperature and number of particles are the same, the only thing we're changing is the volume, we can predict what's going to happen with the pressure. If we look at the first one, we see that this is a smaller volume. We can tell, I'm using kind of distance here, but imagine in 3 dimensions. But if you can see here, we have a smaller volume in the first one and a bigger volume in the second one. And if these balls are just rolling back and forth between the walls, If they're just going back and forth, they bonk into the wall, turn around, bonk the other wall. The first one, it's going to hit it more frequently if they're moving at the same speed. So I will try and like be a metronome here. So I'm hitting the walls at this frequency. And now I'm going to move at the same speed, but I'm going to go a farther distance. And we see how less often I'm hitting the walls and going backwards. Even though I'm moving at the same speed, I have further distance to cover. Therefore, I'm hitting the walls less often. And so smaller volume hits more often, which we will say has the higher pressure. And so the relationship here is that volume, if the volume goes up, pressure goes down, or vice versa. And if you want to think about it going into space, in your cartoon world, there's no pressure in space, right? It's a vacuum. So if you go out into space, what do you see happen in cartoons? But things expand and explode, right? Um, you have people's heads expanding and exploding. It doesn't actually happen that way, by the way. We're not gases, so uh, we are solids, although we are made mostly of liquid, but that aside. The relationship there is inverse between the two. This is an inverse relationship. As one goes up, the other one goes down. So notice we have the smaller volume, it's going to hit the sides more often. If we have the larger volume, it's going to hit it less often. And remember that pressure is how often it's hitting. So large volume, you're going to hit less often. There's more space for you to travel before you hit the wall. All right, and we're assuming that your temperature and number of particles is the same. All right, and so we can say then that mathematically, if one goes up, the other goes down, they go up by the same ratio. And so we'll say that the product of the two is always constant. So if we double the pressure, the volume will have to be decreased by half. If we triple the volume, the pressure becomes 1/3. So they always have to be in balance with each other. So the bigger we make this, the smaller the volume is going to be. I'm sorry, the bigger pressure we make it, the smaller the volume is. And then vice versa. The bigger the volume, the smaller the pressure. So the product of the two is constant. These are inversely related to each other. All right, so hopefully that makes sense. So don't need these. All right. Cool. So let's go ahead and look at our next relationship then. Next, we're going to do temperature, it looks like. So we're not going to actually use this mathematically. And if you really wanted, yes, it's very simple. The constant doesn't matter. It's just a number. But it's suffice it to say, if you double the pressure, you will have the volume. If you multiply pressure by 6, you divide the volume by 6 because they have to cancel each other out. It's constant. All right, let's look at pressure and temperature. So I'm going to put our gas molecules in 2 containers. This one may be a little bit easier for us to see, and hopefully this arrow is representing the speed of the molecules, and that's the temperature, right? So in this case, the volume and moles are identical. I have one particle in there each, so moles are the same. Their distance is the same. So let's go ahead and look at my metronome again. So here I am. All right, so I'm gonna go like this. So this is how frequently I'm hitting the walls. Now I'm gonna do it faster. Going the same distance, but going faster. And so we see I hit the walls more often, right? So the faster you are, the more collisions you have. And so we see that as temperature goes up, pressure goes up. And conversely, as temperature goes down, pressure goes down because things are moving slower. They're going to collide less often. As they are moving faster, they're going to collide more often. And so we see that these have a direct relationship. If one goes up, the other one goes up. If one goes down, the other one goes down. And so, mathematically, we describe this as something like that. If we double the pressure, we have to double the temperature because they would be constant at identical volumes and numbers of molecules. So, or if we decrease the pressure by 1/2, the temperature will also decrease by 1/2. So just be aware also, though, Kelvin must always be Kelvin. We can't use Celsius, right? We'll see how to use these later on. So that's the direct relationship. So one goes up, the other goes down, and mathematically we write those as a fraction. All right, and the last one we'll look at pressure and moles. So in this case, we're going to have our volume and temperature constant, but I'm going to put more particles in one of our containers. And so hopefully we can see, all right, now I've got 2 particles here. They're going to just be bonking more often, right, as they're just going and bonking things. So we see all these, look, I'm dancing. Uh, all these are happening. Look at all these collisions that are happening versus if I just have one bonking into it, right? So more molecules, more collisions. This is, again, pretty obvious to us. And again, you can think of these as like the freeway, you know? The bigger your freeway is, the less collisions you have. The faster things are moving, the more collisions you have. The more cars you have on the road, the more collisions you have. So, third grade logic, a little bit easier to understand than 17th century chemists, in my opinion. So, as moles go up, pressure also goes up. As moles go down, pressure goes down. So this is another direct relationship. And so, hooray, we can assign this the same sort of relationship here. If we triple the moles, we have to triple the pressure. Because we're putting more molecules in, they're going to collide more often. All right, so it's a direct relationship. And these are all multiplicative relationships. So we don't look at, add 10 moles. That doesn't really matter. We look at the difference, or the ratios. So if we multiply moles by 10, we have to multiply pressure by 10 if our volume and temperature are constant. Meaning those aren't changing between our 2 little like examples here. Because obviously, if the one on the bottom, even though it's by itself, if it's moving faster, it'll be hard to say which one has higher pressure, because now we're looking at apples and oranges instead of apples to apples. So let's go ahead and take this information. So we have these 3 relationships that we've just covered. So we've seen that pressure times volume is a constant, pressure divided by temperature is constant, and pressure divided by moles is constant, assuming the other variables are constant as well. But this means that we can clump it all together by saying then that P times V over N times T, so keeping all those relationships the same. The pressure times the volume, the pressure divided by the moles, the pressure divided by the temperature, will equal a constant. And for this constant, we say the letter R, where R is our universal gas constant. And we actually have a value for this because the pressure and volume constant, it doesn't matter because that depends on what the temperature and moles are. So we don't really care mathematically about those three equations above, but this one we do. This one will be extremely useful for us. It tells us all the relationships that we need to know. And so we're going to see that R, we're going to see that R is 0.08206 liters times atmospheres divided by moles times Kelvin. Notice, by the way, look at the units. Liters would be volume, atmospheres is pressure, moles is N, and temperature is Kelvin, right? So we have all of those PV over NT right here in R. We have the formula for us. If we know what units those stand for, we don't need to memorize the formula, but you're going to do it anyway. And in that case, I'm going to help you out by rearranging this. I'm going to make it so we don't have any more fractions. We just have everything on one line. Some people call this the pervert law because PV and RT pervert. They kind of say that, I guess. It's called the ideal gas law. And so it's something that we're going to be using extensively in this chapter. And it allows us, we can relate any quantities to each other to figure out the other one. So that's its extremely powerful equation. If we know pressure, volume, and temperature, we can figure out the moles. If we know the volume, the moles, and the pressure, we can figure out the temperature. If you know three, you can figure out the fourth by using this. And so it allows us very easily to calculate important things. All right, and better than that, it also gives us relationships that we can see. So we saw how pressure fit into all this. It was pressure times volume, pressure divided by moles, pressure divided by temperature. And that all fit in there in that equation. If we look at other ones, we can see, well, let's look at volume in moles. We can derive that from this equation. We can say, let's look at volume in moles. Oh, volume in moles must be divided to be a constant, and so that must be a direct relationship. Assuming pressure and temperature are constant, and that makes sense to us, right? Moles is how many things you have. Volume is how much space things occupy. Does it make sense that the more things you have, the more space you occupy? Presumably. For example, one OChem textbook, two OChem textbooks, they occupy more space if there's two of them rather than one, right? Basic, right? If I have 1 pound of flour versus 500 pounds of flour, the 500 pounds is going to take up more space, right? So we can figure out relationships, otherwise. So, or we can also say that volume and temperature are directly proportional. As the temperature goes up, the volume gets bigger. And we know that things expand when they're heated. So that makes sense to us as well, and they contract when they're cold. So there we go. We can find other random relationships. We can say, how about temperature and moles? That's a little bit less obvious. But at the same temperature, we're going to see that those would be inversely proportional. So the point is you can take any pair of these variables, keep them where they are, P over N, P over T, V over N. You can see all the relationships between all of these things. So it's good stuff. Alrighty. So you can derive any of those gas laws, the Charles's law and the Boyle's law and the Avogadro's law and the Gay-Lussac's law. You can derive them all from this. You don't need to worry about memorizing individual laws. Just use this every time. And so if you don't have a value, if it says like, well, the pressure is doubled, the okay, well, let's not worry about that. We'll look at that in just a second. So this one will take care of all your needs for calculating anything. So let's look at an example. All right, let's see. This would be an example of a problem. So a gas with a pressure of 1.26 atmospheres is in a container. The container is 16.89 liters and it's at a temperature of 299 Kelvin. How many moles of gas? Again, big point. It doesn't matter what your gas is. If this is methane, if this is carbon dioxide, if this is oxygen gas, if it's hydrogen gas, xenon, sulfur hexafluoride. Choose your favorite gas. It doesn't really matter. We'll see it matters when we're talking about grams of gas or density of gas. Those things will matter, but for just something like this, the moles, it doesn't matter what the identity of the gas is. All right, so in this case, we're looking for how many moles, so we can rearrange our equation, and it's as simple as then plugging things in. In this case, I've been nice and everything has the right units. Remember, in order to use this equation, you must have pressure in atmospheres, volume in liters, temperature in Kelvin, and then moles, of course, in moles. So our pressure here, 1.26 atmospheres. The volume, 16.89 liters. R, and then the temperature was 299 Kelvin. Let's look at our units. Always double check your units. Atmospheres cancels out. Liters cancels out. Kelvins cancels out. We're left with 1 over 1 over moles, which is just moles. Bust out your calculator. As always, I've forgotten mine, so here is my phone. All right, let's go ahead and do this. So 1.26 times 16.89 divided by 0.08206 divided by 299 equals 0.86735 moles. And sig fig wise, it looks like we have 3, 4, and 3. So we're going to need 3 sig figs in our answer. 0.867 moles. Exciting stuff. There's really only two ways I can make this more difficult. One is to change all the units into things that aren't the correct units to make you convert. Uh, Alternatively, I can ask for something that's a little bit less obvious. So let's do another one, shall we? Let's do both at once. A sample of xenon in a 612 milliliter container is has a pressure now we have all the wrong units. So we just need to get everything in the correct units. That's all we have to do, and then we can go ahead and plug in our formula. Note that we need liters, atmospheres, Kelvin, and mole in order to make this work. In this case, we're solving for temperature, so we don't really need Kelvin right away. We'll deal with that later. So we need liters. So 612 milliliters. Hopefully we can do this in our heads. 0.612 liters. Great. Atmospheres, we have 218 torr. Remember that the conversion is 760. Okay, 218 divided by 760, 0.2868421. That should have 3 sig figs. Oops, that's atmospheres. And then the last one is we need moles. We have grams. Remember how to convert between grams and moles is molar mass. Xenon has an atomic mass of 131.3. And so we can go ahead and figure that out. In this case, the identity of the gas does matter because we're talking about mass, and each gas would weigh different amounts, right? So 22.8 divided by 131.3, this is 0.173648, and that's going to need 3 sig figs. So now that we have our 3 quantities in their correct units, we can go ahead and figure this equation out. So the temperature is going to be PV over NR. Right, we divide by NR for both sides. And so we're going to get, what's our pressure? 0.2868421, keeping our sig figs for 3. Our volume, 0.612 liters. N is 0.173648 mole. And then, of course, R is constant. Double check our units. Atmospheres, atmospheres, liters, liters, moles, moles. We're left with 1 over Kelvin, which is Kelvin. So let's go ahead and plug this in. 0.2868421 times 0.612. Notice I just have a crazy extra amount of information without rounding just to make sure that we avoid any rounding errors. Divided by 0.173648. So I would do at least two more spaces if you're going to use a before rounding, and then keep your sig figs. That number divided by 0.08206, and so wow, the temperature is quite low. We get 12.31949 Kelvin. Oh, because the volume's okay. Gotcha. Okay, so we have this very cold sample apparently. Must be helium. I guess xenon. Well, whatever. It's a fake problem. So I make up the numbers is what happens. All right. So since, however, the problem asked in Celsius, remember that degrees Celsius is Kelvin minus 273.15. So we take that number, 12.31949, which should have 3 sig figs, subtract 273.15, and so minus 273.15 equals negative 260.8 degrees Celsius. And that would be our answer, with the correct sig figs in the ones place. So don't forget, even though none of these numbers had 4 sig figs, our answer can still have 4 sig figs because of addition rules. Or in this case, subtraction, but same thing. Right? We would need to block off our number at the tenths place, sorry. And so that'll be our value. All right, so don't forget your sig figs. It's a very easy place for me to take off points for sig figs, so don't forget them. All right? So that's as hard as these get. It's as hard as these get, is relating different units with these. So it's not that difficult. Another way we can use the ideal gas law is to make comparisons. So the ideal gas law as written is for figuring out the fourth quantity when you know 3. But what about when things are changing? Since we know that PV over NT is equal to R, and we know that R is equal to PV over NT for anything else, remember the identity of gas doesn't matter. It's constant. It's universal. We can say, well, that just means that our set of conditions, number 1, whatever those happen to be, are equal to R, as are our conditions at our second time of measurement. So if we're moving the gas to a different container and changing the pressure and seeing what happens with the temperature or whatever, we can do that. We're going to use this to see what happens when things are changing. And so as a result, we can combine these, say P1V1 for any set of conditions. Oftentimes, you will see this as omitting the moles, because very often you're looking at the same sample of gas that's being treated in different conditions. So very often, if your moles are constant, just leave them out. No problem. Or leave them in. It doesn't matter. If you have 1.24 moles on both sides of the equation, it will cancel out. So it doesn't matter. So let's see how to use this. Actually, I'm going to say grams, because why not? So give me a sec to write this question out. A 1.29 gram sample of oxygen is moved from a 2.20 liter container at 25 degrees Celsius with a pressure of 1,000 torr to uh, a 10.2 liter container at 4 degrees Celsius. What is the new pressure? So notice, by the way, we have a lot of numbers here. And we just need to be consistent with what we choose to label these. So without worrying about the units necessarily, this is N, right? It's our amount of sample. This is a volume. It's got a liters. This is a temperature. This is a pressure. This is a volume. This is a temperature. So look at the units, assign your quantities to them. And let's go ahead and choose which one to be our first set of conditions and which to be our second set of conditions. So we're going to say, well, this one's in this container at this temperature with this pressure. Those are all related. Let's say those are 1. And now it's moved to a second container at a second temperature. And what's the new pressure? Well, that will be pressure 2. Notice that there's nothing about removing any amount of this gas. So all this information here is irrelevant. We don't care. We see that volume, temperature, and pressure are given to us. Volume and temperature are changing. We can figure out what the new pressure is going to be. The moles don't matter here. You can include them if you really want, but that's going to be more. We'd then have to convert this into moles, and then we'd have to worry about including that in our calculation. It's just easier not to. So read your question. If it says something's not changing, or if it doesn't say something is changing, then just leave it out of your equation. So if we're just taking the volume of something and changing its temperature, the pressure is the same, then leave pressure out of your equation. In this case, moles is staying the same, leave moles out of our equation. So if we leave moles out, we can do that. And then let's just say let me give you a unit to solve for. Okay. So with this one, it doesn't matter what our units are except for the temperature. Temperature must always be Kelvin. Let's go ahead and rearrange this equation to solve for P2. If you do that, you get this. Should be very easy for you to rearrange this equation, just solving for P2. Any units are fine. Liters are okay, milliliters are okay, whatever, as long as they're the same unit. Does not matter what units you use. The only thing that you must be sure to change is Celsius. You can never, ever, ever use Celsius. Here's why. I'm going to change the question. We'll put it at 0 Celsius. If we just try and say, well, P2 is equal to pressure 1, which is 1,000 torr, V1, 2.20 liter, 0 degrees Celsius, volume, temperature 2 is, temperature 1, 25, or V2 is 10.2 liters, we get 0. Worse, what if temperature 1 was 0? Pressure can never be 0. It can also never be negative. So that's a hint we did something wrong. So we can never ever use Celsius. So we've got to convert those to Kelvin. So 0 Celsius, hopefully we don't need to do the math. It's just 273.15 with an underline under the 1, Kelvin. And then the 25 is just going to be 298.15, just adding 25 to 273.15. So notice our units here. Kelvins cancel, liters cancel. We're going to be left with torr as our unit. And let's do it. 1,000 times 2.2 times 273.15 divided by 298.15 divided by 10.2. And we get 197.6 torr. And looking at the sig figs, we're going to need 3 sig figs here, so 198 torr. And let's look at what unit I asked for, millimeters of mercury. Remember that millimeters of mercury and torr are identical units. So 198 millimeters of mercury. be our answer. And let's see if we can predict this. So we're going from a smaller container to a bigger container. So we're expecting pressure to go down. We are going from a warmer temperature to a colder temperature. So we would also expect pressure to go down. And notice our pressure did indeed go down. We had 1,000 torr to begin with. We ended up with about 200, so we definitely went down. So it's always a good idea to just double check, does your answer make sense? Um, you should be able to kind of justify it, right? So we are expecting, for these two reasons, um, we're expecting a decrease in temperature overall, all right, for our same sample of gas. Alrighty, fun stuff. So we have a few more things we can do with this equation. If we wanted to put molar mass into the equation, we can figure it out. We can figure out the density. And, if you guys really care about the derivation, I can talk about that, but let's just talk about density. So density would be mass per volume, right? In this case, we're looking at grams per liter. Um, doesn't matter, or it matters what unit we use, but we're going to see how this will work. We can figure this out using our ideal gas law. So if we want to solve for grams per liter, that would be our density. Well, we know that PV equals nRT. And so if we want to work with this, we know volume is already in liters, but N is in moles. And how do we go from moles to grams? Well, it's divided by the molar mass, right? So we know that molar mass so if we divide both sides of this equation by the molar mass, remember that N over molar mass will be just grams. So PV over the molar mass equals grams times RT. If we want to rearrange this such that we have grams per liter, grams over volume, we can do that. We can move RT to both sides. We can divide both sides by RT, and we can divide both sides by V, right? If we want grams per liter, grams over volume, that would be P over MRT, right? So since we're dividing both sides by, actually, I'm sorry, we need to, this should have ended up in the numerator. What have I done wrong? Oh, that wouldn't cancel. We need to multiply them. I'm sorry. Just kidding. So because moles needs to cancel out, right? Moles times molar mass equals grams, not divided. So I should have written out my units. So we're going to see that the density will be equal to the pressure times the molar mass over RT for any gas. So the density of the gas here we can relate to the molar mass as well as our sample. So we're going to see that the higher your molar mass goes, as your molecules get bigger, your density gets bigger. That's the idea here. And so we can calculate it. We can see what the density of a gas will be at a given temperature. What is the density of O2 at 1 atmosphere and 300 Kelvin? We can figure this out. We know that pressure, I'm sorry, not pressure, that's density, rho. I'll try to make that a little bit more obvious. There we go. Rho equals 1 atmosphere, 32 grams per mole, 0.08206 liter atmosphere, Kelvin mole, 300 Kelvin. Notice the units cancel, moles cancel, atmospheres cancel, Kelvin cancels. We are left with grams over liters, which is density units, right? Mass per volume. And so we can figure it out. 32 divided by 0.08206 divided by 300 will be 1.299, too many sig figs, so 1.30 grams per liter. Done. Simple. So just another equation for us. So it's just solving this thing for grams per liter. And so that's one thing we can do with it. So we can relate density and molar mass as well using the ideal gas law. All right, and so we can do all this sort of fun stuff. So next time, we'll talk about temperature in more detail. We'll talk about how gases behave, what the assumptions we make are about their behavior, and then we'll see some corrections for real life behavior, because this is the ideal gas law, right? It's when things are ideal, but in reality, things are not ideal, so we have some small corrections to make. So go ahead, have fun. We'll see you on Thursday, and we'll continue with this. Take care.